The main reason I introduced Python was that it's a nice way of writing language bindings. But before we get to the actual language binding part, let's ask ourselves the question, why? Why would I want to write a language binding? Python is often used as a glue language. We can combine the ease of an interpreter with calls to performant libraries, like in NumPy when we call the matrix multiplication, which actually then uses all the cores and the vectorization and other things our processor is capable of. So there are a couple of reasons why we might want to use language bindings. Like in NumPy, we want to use optimized code that already exists. Some Fortran code or C++ code that has been developed in our group for years. But now we want to give it a more modern look. And rather than modernizing the C++ code, which would also be a good idea, we write Python bindings. If we have been doing workflows from within Python using maybe popen, where we actually call a binary, we can improve performance by reducing the overhead of actually starting a separate program and communicating through pipes. We can actually pass the arguments that we want to a proper wrapper. And a nice wrapper can also simply lead to cleaner code. Before you get started with the notebook, now it's actually the time to run the build script. But we can do that after the lecture. There are various ways of calling compiled functions. Actually, Python comes with an inbuilt way, C-types. C-types was originally developed for calling Windows functions. And I don't like it, so I'm not going to introduce it to you. I never claimed I would cover everything. However, the foreign function interface, I think, is a fairly nice way of wrapping a single function call. So let's look at a function definition. And I hope even those of you not familiar with C will understand what's in here. I define a function called work frequency, which returns an integer and takes a file name as input as character star, and a word also as character star. So the idea is it looks for the occurrences of the string given in word within the file given in file name. Sounds like a useful function. How could we call this function from Python? We import CFFI, and then we generate a foreign function interface object. So here I have my foreign function interface, cffi.ffi, and I pass it the definition of my function. And if you look at it carefully, this is exactly the same definition that we had in the header file. So it's not hard to get. Then we call, or we open the dynamic library that this function is in. In this case, you just build it, and it's called libtext_stats.so. And then we can call this function as ts.wordFrequency. So it gets the name actually from our function definition here. B quotation marks test.text, comma, and then B again for the U. We need to use byte types explicitly in Python 3 because only those map properly to char star. If you just have a single function that you need to call, I think this is a perfectly valid way of doing it. Very little overhead. You basically just have to have the function definition, and you need access to a dynamically loadable library. Question?
What with library, or even with the normal sweep? It has to be compiled the sweep as a library.
The question was if it has to be compiled as a library to be used. Yes. I have to be able to load it, so it has to be a dynamically loadable library. Yep. What if word frequency had been written in Fortran? We could actually do the same thing. But let's first look at the ISO-C bindings of Fortran. Since Fortran 2003, so if you use Fortran, even there you should get to more modern versions of Fortran. Fortran provides ISO-C bindings as a module. And this actually lets you define exactly your C interface. How will Fortran functions look to C? And so here, for example, we say it's a C character, length equal 1, intent in, file name. And here the same for word and word frequency. Now we have a well-defined function called word frequency. And we could also actually define here the function name if we wanted to give it a different one. So that actually has become quite useful. For the CFFI interface, you'll see how it works in the notebook for Fortran, but it's basically the same as for the C function. So Python generates C code, and the C code is compiled. So there's nothing stopping us to call C functions from within Python. And that's really all a wrapper does. It calls the underlying native function that we want and makes it available to Python. And Python can do that. So in Python, we would actually import the header itself with the cdef extern from text_stats.h, and could then define a C and Python definition of word frequency. And if we do that, then we can call word frequency. But we still have to make the byte type explicit, which I find ugly. I mean, I want to be able to just write text.text and you, not be text.text and be you. I want to be me. Anyway, so we need to do a little bit of work here. We need to actually adapt the type. And that's where, to me, bindings come in. So for me, proper Python bindings are not just a way to call a C or Fortran function. It's a way to call them in a Pythonic way with Pythonic data types. I want to be able to use something that doesn't look out of place when it's in my Python code. And for that, I have to do a little extra work. So here I still define my word frequency. I could have more functions in this text_stats.h. Then these would actually define the ones that I'm making accessible to Python. So I don't have to make all of them accessible. I can pick already here. Then I define here a function word frequency, which will be a Python function that takes a file name and a word. And I use Python to actually encode the file name using UTF-8. So if I have a UTF-8, so Unicode-capable file system, that would be the proper way to do it. Then here I have the file name properly encoded, the same here for the word. I can then set those equal to the C types, both of char star, and call my word frequency. So I do some conversion here within Python, going from a regular string to a byte encoded string. But I do that once when I write the bindings. I don't have to do that within my Python code. So my Python code looks much nicer. And that, for me, is a really important part, I'm going to repeat this, in writing bindings. It's not just about making the calls accessible. Now, we can't just wrap C code or Fortran code. We can also write wrappers for C++. So for this, I picked a very simple point3D class. It has two constructors, so two ways of generating a point3D object. One just takes the coordinates. The other one takes a vector. Vector is a standard data type within C++. I have a function translate, which also comes in two variants. One's taking the individual arguments, the other one taking a vector. And I can get the coordinates. My data is stored in some private variables, x, y, and z. So for stars, I'm only going to wrap the point3D x, y, z, and the translate dx, dy, dz, and actually the coordinates, so that we can check that it did something. The first thing to notice here is my import. Python knows about most of the standard library, or at least the container types of the standard library of C++, and knows how to map them to Python types. So here, for example, I am importing the vector type, the standard vector, as vector. I'm getting here my point3D header. And just like I did for the function, I have to tell it which class and which functions I actually want to import. So here are the the constructor and the two functions that I just mentioned. Standard vector is a so-called template library, or a templated container. It can work with different data types. In Python, this is expressed with these square brackets. All right, so I have point3D, translate, and coordinates. Now, to get to my Python class, I actually need to have I can use a CDEF class, PyPoint3D, so it's a thin wrapper around my C++ class. I have two additional functions, cinit, which is called whenever I construct a point3D object, a PyPoint3D object, and that's responsible for doing the C initialization. So whatever I need to do within C++, like getting a new point3D object here, will be done within the cinit. And it's customary to keep a reference to my object in self.thisPointer. The dialog is called when the variable is going out of scope to make sure that everything is properly deallocated. So this will actually also call the destructor of the C++ class, and if it's written in a proper way, it will get rid of the object and free the memory. So we can now construct an object of that type just by writing origin equal PyPoint3D000. Our data is actually stored in the C++ structure. So the x, y, and z variables that we saw in our C++ class are what's holding the x, y, and z variables here. Now, that's the Python way of doing the bindings. And if you come from Python, I think that is actually the nicest way of writing bindings like that. If you're also an experienced C++ programmer, or you're actually writing the C++ library, and also want to provide Python bindings, PyBind 11 is a very nice alternative. PyBind 11 came from Boost Python. Boost is a very large C++ library where people try out different things, algorithms, containers that have not made it into the standard yet. And one of the modules that was there was Boost Python. Boost is also a large library. And the guys that started with PyBind 11 wanted something a little more lightweight. So they took Boost Python and removed everything that needed Boost from it. That was the starting point of PyBind 11, and they moved on from there. So by now, those two branches actually have diverged. So this is what PyBind binding to a simple function looks like with PyBind 11. So we're going back to our word frequency. We include the PyBind header, and we include the text_stats.h. This extern C is needed because this is actually a C function. Don't worry about it. This is a macro that helps set up a Python module. We take the name, text_stats, and this is then a reference later for the module. So with M, we can access the module that's being created. For example, we can set a docstring for the module. So here I'm saying the docstring for the module is some functions that provide statistic information about a text. When I call later the function and did, for example, in a Jupyter notebook the question mark, I would get this docstring for the module. I also define my functions, here word frequency. This is a reference to the original function pointer, so what I'm going to call. And here too, I can pass a docstring. This part here, the R quotation mark doc open parenthesis, is actually what indicates a raw string in C++. So this goes over multiple lines. All the line breaks and all the spaces are actually part of the string. So this will generate a nicely formatted docstring that can be read by IDEs, by Jupyter notebooks, or just your regular Python shell has the help function. So how do we use this extension? We import text_stats, our new module. And we call, since I didn't import word frequency, we call it from the module as text_stats .word frequency text.text and u. Magic. It automatically generated a wrapper that actually does the proper translation from a string into the character star that the C function needs.
Automatically manage the incorrect.
It converted it automatically from the Python string to the binary representation. Yeah. And really, there wasn't that much C++ syntax in there. If you have a more complicated wrapper, you might need to work a little harder. But let's start by looking at a class. So we still have our point3d class. And I'm including the header. I'm also including now pybind11.stl.h. And I create again a docstring for my module, a collection of functions, objects to deal with 3D points. Here I actually define both constructors. So my first one is takes the 3 numbers. The second one takes a standard vector as an argument. I also have my translate function. It's called translate, and here again I pass the function pointer, giving it the signature of the function and the pointer. And again, a doc string. And I'm doing the same thing for the coordinates. And you'll see that you can then call it, import the module, and call your points, translate them, and get the coordinates just like before. So I think even if you are not that deeply into C++, for simple cases, this is still a simple way to generate bindings. One nice thing about PyBind, I was saying that Python knows a lot about this C++ standard library. PyBind, on the other hand, knows a lot about Python data types. It knows about lists. It knows about maps. So you can actually use Python lists and Python maps within C++, which makes doing the data mangling that you might have to do to convert between what your C++ or C function needed and what Python provides much easier. So you could, for example, write an entire C++ function that returns a Python list. Question?
Let's suppose that my C code is parallelized with OpenSCC library. If I
This is going to be a longer question.
if I compile with
Please repeat.
If my code is parallelized with OpenSCC, and I would like to compile with then create the wrapper for PyBind and use Python, then I need to compile it with, for instance, in my case, PGI compiler. Does it work, or it's because I tried to do several times, but I was never able to do it using my wrapper. So it's I'm pretty curious if it's easier.
I haven't tried, so that's the first part of the answer. You should be able to use PyBind 11 with the PGI compiler. I don't see why it shouldn't work. And there's nothing really in OpenACC that would prevent us from calling it from Python.
Yeah, that's.
So I think, yeah,
because
it should
it's
work.
like OpenMP. OpenMP works very well for me with GCC, but OpenACC with GCC seems to work very well. So it's
Well, it's not as developed yet. That is true. You should give it a try.
yeah. Thank you.
Is there an overhead of wrapping these and calling? Yeah, by dynamic library and yeah.
Is there an overhead for wrapping and calling the dynamic library? Yes, every function call has an overhead. Is it relevant within Python? No. So PyBind generates very efficient wrappers. Yes. More questions? No? How many Fortran programmers in the room? All right. Now, I was just advocating that you should use newer versions of Fortran. However, the next thing that I'm introducing works best with Fortran 77 to 95. But if it works, it's a great way of generating bindings. It's called F2PY. F2PY is part of NumPy. And it can take Fortran code, like this one, where I also created a points module. It has 3 arrays, x, y, and z, and some routines that act on these arrays. So here, for example, I initialize the points, and here I'm just getting the coordinates. Now, writing a wrapper for Fortran, by the way, does work with Python as well, but that's it. So one line And we can do this. From points underscore f, that's just the name I gave this module, import points. I can now initialize one point, set its coordinates, translate them, read them. Oops, there was one too far. And actually, I could now output x, y, and z. Look at this. I'm returning a tuple. And I'm unpacking it from Fortran. How does it do this? Oops. Let's look at the code again. For example, here. So coordinates actually takes multiple arguments. Here, I give the intent as in-out. So the variable both is used to take a value and to return one. Tx, ty, tz are only intent out. So if it's intent out, it actually generates a Python wrapper that does not take them as an argument, but just returns them as a tuple. Too fast. So it takes one argument and then returns my tuple. So if you use Fortran 90, Fortran 95, you have the intent, and F2PY is smart enough to generate proper bindings for that with a single command. By the way, you can also filter. So if you don't want to get all your functions that are in your Fortran code, but just specific ones, you can tell it which ones to use, which ones to leave out. That works quite nicely. But what do we do if we are still stuck with Fortran 77? Question? It's a reference. It will actually be treated as a reference. The question was the in-out argument. Why is it not returned in the tuple? It's actually treated as a reference. What do I do when I have Fortran 77 code? No intents. How do I generate proper bindings out of that? Well, that's what CF2Py comments are for. Since I can't write it in my variable explicitly, I use a comment. C starts a comment with a specific name. And F2PY will look for those comments, look for what's given in there, and actually generate then the proper bindings. So here, for example, index and n are taking as input arguments, so are dx, dy, dz. The output or in-out is x, y, z, so those are given then as references. And that's what the translate function here does. So with the comments, the F2PY comments, I can generate Python bindings that are just as good as for Fortran 90 and Fortran 95. All right. Questions? More questions regarding the bindings? No? Then it's time to move on to the notebooks.